All right, everyone. Today we are moving on from graph sketching, and we're going to learn about two more major theorems in calculus. So if you think back, you've already learned about the intermediate value theorem. I'm sure if you went back in those orange flip books that you've been dutifully filling out, you could refresh your memory on that. So we've already talked about the intermediate value theorem. Today we're going to talk about two more. One is going to be the mean value theorem, and then we have our extreme value theorem. So first we're going to start off with the extreme value theorem. And if you think back to graph sketching, right, when we're talking about extreme values, right, extreme values, those are just our max and min values. Okay, so this theorem is all about if and when those max and minimum values are guaranteed to occur. So we know how to find extreme values for functions. So we're able to pick them off a graph at this point. We can find them if we're given the equation for a function or its derivative. We've had lots of practice with that. But really our question now is how we know if a function even has any extreme values, or how can we guarantee that it would have extreme values? So what our theorem says is that f is continuous on a closed interval from a to b, then f is guaranteed to have both a minimum and a maximum value on that interval. Okay, and so just like when we talked about the intermediate value theorem, and I know people weren't really happy about having to write out these conditions and explanations, but that is going to be super important as we're looking towards the AP test, that we're able to identify the conditions and correctly explain why a theorem does or does not exist. So we'll be working on that as we go through the examples today. So if I look at my three examples here, you can tell in each case I am closed on that interval from A to B. And so really I don't like where these points are, but these endpoints should be here and here, and then let's go here. Okay? And so if I look, I'm closed on each of these on an interval from A to B. Now, they definitely have different behavior, but as we go through, we should see that each one has at least, at the minimum, at both a maximum and a minimum value. So if I look at this example here, let's find where our max values are. And now we're talking relative and absolute. So if I look, based on everything we've done so far, hopefully we can pretty quickly pick out that we have a maximum value here and here. So at x equals c and x equals b. And then on the other hand, I have some local minimums here and actually an absolute minimum here. Now, on my next example, right, I don't have all that curvature of the graph, but because I'm defined on this closed interval, I do see that I have a max at x equals a, and then my minimum at x equals b. So again, despite the fact that I don't have all that curvature, I'm still guaranteed those max and min values because I'm defined on that closed interval. And so then last for my example here, I have a maximum at x equals c, and then I have my minimums at x equals a and b. So those were all defined on that closed interval, so we knew that we were guaranteed those maximum and minimum values. But more likely, the type of questions that you're going to get are going to look like these down here. So the directions say to determine whether the EVT, the extreme value theorem, applies to the graph of these functions on the interval from 0 to 2. And explain your reasoning. And this is what's going to be so important when we get to the AP test, and why I'm always kind of harping on having these explanations down. Okay, and then secondly, if possible, we're going to identify where the maximum and minimum values occur. So the important thing to note here is even if the extreme value theorem does not apply, it doesn't mean that you're not going to have any maximums or minimums. It just means you're not guaranteed those values. So let's look at number 1. So I'm looking on the interval from 0 to 2, and I notice that I'm continuous on that closed interval. So I would say that the EVT applies because our function, we'll call it f of x, is continuous on the interval from 0 to 2. So what we're showing there is that we know the conditions for the extreme value theorem to apply. We know it has to be continuous over the closed interval. So that's our first part, determine whether it applies, and then explaining our reasoning. Now the second part, we can go ahead and look where our maximum and minimum values occur. And so here it's pretty easy to pick out our max is at x equals 2, and then our minimum occurs where x equals 0. Okay, I'm going to draw a line here to separate these problems. Now on my second one, again, I'm determining whether the extreme value theorem applies. So I have to go back to my conditions. I'm always going back to those conditions to see if I can even use this theorem. So again, if I go back here, we said that f of x, or f, had to be continuous on a closed interval. So if I look at my graph, it looks like I'm pretty continuous. There's no jumps in between, but I'm not defined on that closed interval. So right away I know that EVT is not going to apply. So I say the EVT does not apply because f of x is not continuous on a closed interval. So not continuous on the closed interval from 0 to 2. Now again, all that means is we're not guaranteed both a max and a min. However, if I look at this, I clearly still have a max at x equals 2. I can't identify a minimum because I'm undefined at that point. So last but not least, again, we have a situation here where we're clearly not continuous and we're not defined on that closed interval. So again, we would say that the EVT does not apply because f of x is not continuous on the closed interval from 0 to 2. So now we check, well, do we have any actual maxes or mins? So if I look, I don't actually have a max value. I can't pin down that maximum because I'm open at that point. So all I'm left with is this kind of local minimum at this endpoint here. So I do have a min at x equals 2. So that's our extreme value theorem. Again, if we're continuous in closed, or we're continuous on a closed interval, then we're guaranteed a maximum and a minimum value on that interval. Now again, it doesn't tell us where that will occur, but we can just guarantee that we have one. So let's move on to our next theorem. Okay, and this one's called the mean value theorem for derivatives. And something that might help you out here is when we think of means, finding the mean in math, we're talking about finding the average. And so we're going to use that idea as we go through this theorem. So what this theorem says is that if y equals f of x is continuous, here's some of our conditions. It's continuous at every point of the closed interval from A to B. And so I have a second condition, and it's differentiable. okay, at every point of its interior, so it's differentiable on that open interval, then there is at least one point C in that open interval at which, and here's how it goes, f prime of C is equal to f of B minus f of A over B minus A. So that's what the theorem says, and we're going to talk about what that really means. Hopefully, as you're looking at this, we're realizing that f prime of C, that's just the instantaneous rate of change. So that's our instantaneous rate of change at x equals C, right, or the slope of the tangent. And on this side, this is just the average rate of change. On that interval or over that interval. And I'm going to add that's the slope of the secant. Right, this one was the slope of the tangent, so I'm going to add that back in. Okay, so when we talk about, okay, well that's all fine and good, but what does that really mean? What that means is that at some point C in our interval, so at some point C in our interval from A to B, the average rate of change is equal to the instantaneous rate of change. Okay, so all it's saying is that there exists a point such that the average rate of change is equal to the instantaneous rate of change. And I actually think it helps a little to see it graphically. So if I sketch a quick graph here, and let's say it does something like this. So here's A, and here's B. So I'm going to go ahead and sketch in my average rate of change over that interval. So if I do that here, I'm just going to sketch in. So we know that's the slope of the secant. It connects those two endpoints. Right? So there's our average rate of change. So this is our f of B minus f of A over B minus A, right, which is our average rate of change, or the slope of the secant. Those are all the same things. I know that I can pick a point on the graph, and I'm just going to have to estimate it, but there's a point on that graph, and it looks like it happens like about here, where that average rate of change is equal to the instantaneous rate of change, which is just really the slope of the tangent. So those rates of change, those slopes, are the same. So this is f prime, and we call that point where that happens, that's our point C. So that's our f prime of C, or our instantaneous rate of change. So there's a point where the slope of the tangent is equal to the slope of the secant. That's what this theorem is all about. So let's go ahead and look at what a question might look like. So with all of that in mind, here we go. So number one says, show that the function f of x equals x squared satisfies the hypothesis of the mean value theorem on the interval from 0 to 2. So again, what the AP graders are going to look for is that you know those conditions of the mean value theorem. Right? So I would say MVT applies because f of x equals x squared is continuous on 0, 2, right? And I know that because that's a polynomial, and polynomials are continuous everywhere. So it's continuous on 0, 2, and it's differentiable, right? There's no corners, cusps, discontinuities, anything like that. It's differentiable on that open interval from 0 to 2. And again, it's extremely important to state both of the conditions. So I've stated it's continuous on the closed interval and it's differentiable on the open interval. So that's just stating that it actually applies to our situation. Now we actually have to find a solution C that satisfies this mean value theorem. So again, we know our premise here is that f prime of C is equal to f of B minus f of A over B minus A. Now, in our case, right, we know our interval, A to B, is from 0 to 2. So that's our A and B. I also know here, if my function is f of x, my derivative, f prime of x, is just 2x. So if I'm talking about f prime of C, that's just substituting C for x, and I now have 2c equals f of 2 minus f of 0 over 2 minus 0. Well, f of 2 is just 2 squared. So I'm going to move up here. I have 2c is equal to f of 2 is 2 squared, which is 4. F of 0 is 0, so 4 minus 0 over 2. So if I simplify, 4 over 2 is just 2, and then I divide and I get c equals 1. So what that means is that x equals 1, my average rate of change is equal to my instantaneous rate of change. So at that point, we've answered both parts of the question. We've shown that it satisfies the conditions of the mean value theorem, and we've found the value of C, where that happens. All right, so the last question here is now we have a car that's accelerating from 0. It takes 8 seconds to go 352 feet. And it's asking if there's any speed at which we can guarantee that the car must have been traveling. And we need to justify and explain our answer. So here's the idea. If we know the car is accelerating from 0, from 0, and it takes 8 seconds to go 352 feet, we know the average rate of change, right, is 352 feet in 8 seconds, which gives us an average rate of change of, what would that be? 352 divided by 8, 44 feet per second. Right, so that's our average speed. Now, when we talked back, we did the odometer example. We said that a car driving would be a continuous function. So we know that it's not going to skip any speeds. It has to go from every speed from 0 to, between 0 and 44 feet per second. So if this average rate of change is 44 feet per second, we can guarantee that at some point the car must have been traveling at some point the car must have been traveling 44 feet per second because the MVT guarantees that at some point the average rate of change, or the average speed, is equal to the instantaneous speed. So that's just kind of application of that theorem. Again, they're not asking us when that happens. We don't have a way to find that out, but we can guarantee that occurred at some point during the trip. So that's where we're going to leave the notes. The next, tomorrow when we're in class, we'll go through the notes on the next page to really look at all three theorems and make sure we understand the conditions and how we would write the wordings, what the problems might look for, and how we would justify them. So that's it for today.